want to refer back to my previous video on advice for learning mathematics. Make sure you have seen that video before watching this one. Here we're giving a quick overview of the subject of calculus as it's usually understood in the undergraduate mathematics curriculum. Historically, the word calculus has been used in a more general sense for any kind of notational system for computing something by hand, usually by hand. Even something as mundane as longhand division would be an example of a, quote, calculus. The word calculus just refers not to the theory or explanation for why some method works, just the notational system for getting numerical answers in practice. Our modern-day courses in differential and integral calculus provide the best known example of this. So nowadays, the word calculus has pretty much taken over that whole meaning. From now on, I'll be using the word calculus in this restricted sense. So what is this celebrated subject of calculus? First of all, calculus takes us beyond college algebra and trigonometry, the pre-calculus classes, which are usually considered as preparation for calculus. But calculus is certainly not the pinnacle of human knowledge. It is very far from even the high point of undergraduate mathematics. It's often studied in high school. College is, however, a good place to study calculus if you have the prerequisites. Why should you take calculus? Or should you? Maybe you are currently in a calculus class. If so, why are you there? What do you want to achieve from learning calculus? When I teach calculus, I usually stop during the first 10 minutes and ask students why they're there. Within a minute or two, an honest student will say, "Calculus is required for my major." Most of our students, by the way, are not math majors or even students of engineering or physical sciences. Many are in the life sciences or business and finance or social sciences, maybe even theater and art. Some have always just been good in mathematics, and they just want something that will look good on their transcript. Some have signed up for calculus because of encouragement from their friends and families who maybe feel that calculus is just something everybody should take. But for students who are taking calculus in order to fulfill a program requirement, we can ask why their program requires calculus at all. In some cases, like physical sciences and engineering, this may be clear. In other cases, not so much. It's generally worth clarifying that while an understanding of calculus will help you see things in new ways, most students who take calculus will not use the actual content of a calculus course ever again after they graduate. So why do so many programs require their students to take calculus? So let's be honest, there is some evidence that students who do well in calculus will also do well in a great many other endeavors. We can hazard a guess that many programs use calculus as a filter for students in their program. I cannot swear that this is happening in all cases, but when I teach calculus, I'm conscious that the most important lessons that students can learn in our courses have little to do with a specific content in calculus. The most important skills to be learned are to be able to reason clearly and to be able to communicate effectively and clearly. Remembering, as I said in my previous video, that communication is two-way. We expect students to be able to learn by reading and listening, but also expressing themselves clearly in both writing and speaking. I'm not making this up. This is a very short summary of our goals for educational outcomes as summarized on my department's homepage. Your university probably has something very similar on their homepage. We are preparing a generation of teachers, lawyers, journalists, writers, healthcare workers, business owners, entrepreneurs, politicians, social workers, hairdressers, and so on, all of whom must learn to communicate effectively, to work in teams, to participate in society, etc. Keep all this in mind when your calculus instructor gives you a B for an answer that you thought was perfect, because 7.9 is, quote, the right answer. The right answer is seldom a number. Usually the right answer is an explanation. Calculators can give us numbers, but it takes a human to explain what it means or how one gets it. We, as instructors, are striving to teach students not to do what calculators do better, but rather to understand and to communicate. Now, a few questions in your calculus textbook can be answered with short numerical answers, but most cannot really. And any teacher who is doing their job properly will grade you partly on your spelling, grammar, punctuation, and correct use of vocabulary, as well as by correct use of mathematical notation. It will be an abrogation of our responsibility to grade a simple numerical answer without considering the quality of your written explanation. The standard for exposition in mathematics is higher than in any other area. Now, calculus instruction today has become very streamlined and standardized. Let's consider a typical calculus sequence of usually 3 courses, sometimes it's 4 quarters. Sometimes calculus is taught with a focus on the applications to a particular discipline, such as business and finance, or life sciences, using examples from biological modeling and epidemiology, maybe chemistry, etc. A very traditional approach emphasizes the applications to physics and engineering. And it's these that I will emphasize most in my videos. The mathematical notions are the same regardless of the choice of application area featured in the examples, and the most popular textbooks have worked examples and exercises from a wide variety of disciplines. But the examples from physics and engineering figure prominently in the historical development of calculus, and anyway, the ideas transfer pretty well from these to other disciplines. Another distinction seen in many calculus textbooks is the early versus late transcendentals approaches. To explain, think of the different kinds of functions you can compute on a modern scientific calculator. Algebraic functions, including polynomial and rational functions, also square roots, cube roots, etc. And the elementary transcendental functions like exponential, logarithmic functions, trig functions like sine, cosine, tangent, etc. Also their inverses. The late transcendentals approach to teaching calculus uses a more limited palette of algebraic functions for its examples. That way students can concentrate on the new notions of calculus without the distraction of having to worry also about the full set of transcendental functions. Later in the course, the derivatives of the exponential and logarithmic functions would be covered, since these are pretty important both in life sciences and applications to business and finance, although not so much the trig functions. The early transcendental approach makes full use of elementary transcendental functions from the very start. This is the approach that I'll be following in these videos, so that we can begin applying calculus in the kind of situations we really care about in the physical sciences. Now, calculus textbooks often contain a quick refresher on these kinds of functions as a handy reference, maybe in an appendix or the first chapter. But most calculus courses will assume that you already have this pre-calculus material under your belt. And the lectures will begin with the actual calculus content, which is to say, limits. Whatever range of functions you use, it is important to understand the notion and notation of functions. This includes domain and range, composition, one-to-one and onto inverse functions, graphs of functions, etc. All the usual notions that come with functions. You should also understand that the elementary functions listed above, both the algebraic and elementary transcendental functions, are still a very small subset of the real-life functions that we care about. Real-life functions are much more complicated than these. A real-life function might be the output of a seismograph or an EKG machine or the temperature or maybe the Dow Jones Industrial Average as a function of time in a given month. Maybe it's the actual odometer reading of your car during a road trip. These are all important examples of functions, and none of them can be built up from the functions on our list. They are neither algebraic nor elementary transcendental. Now, the reason for our list of limited functions is that these are the easy functions for which simple rules can be worked out for computing derivatives. This allows us to have a reasonable supply of examples on hand when starting to learn calculus, not that these are the most important functions. In a traditional 3-course sequence, the first 2 semesters typically cover single variable calculus. That means calculus for functions of a single variable, something like y equals f of x. Temperature is a function of time, something like that. Here there are actually 2 variables, one input and one output. The input variable is the independent variable, the output variable is the dependent variable. Single variable means only one input and one output variable. And the third course in the sequence would typically be multivariate calculus, meaning calculus of functions with either multiple input variables or multiple output variables, or both. For example, multiple inputs, one output. Temperature is a function of x, y, z for the temperature in a 3-dimensional region in space at the point x, y, z. Or maybe temperature is f of x, y, z, t for the temperature in a 3-dimensional range at a point x, y, z and at the time t. Or how about one input and multiple outputs? An example, r equals r of t equals x of t, y of t, z of t for the position of an object in space, the x, y, z coordinates of an object in space at time t. Then we go to multiple inputs and multiple outputs. So velocity v of xyz equals v1 of xyz, comma v2 of xyz, comma v3 of xyz. For the wind velocity at a position xyz in some 3-dimensional region of space. Here, v1, v2, v3 are the components of the velocity vector in 3 spatial directions. Of course, all this is for a fixed instant in time. However, if the wind velocity also depends on time as well as position, then we must include also a 4th variable as input, representing time. Well, those are just some examples from multivariate calculus. The 2 main branches of calculus are called differential calculus and integral calculus. Calculus 1 introduces derivatives, the main concept in differential calculus. A derivative is a rate of change, specifically an instantaneous rate of change. For example, in the context where temperature depends on time via the simple equation, temperature T is f of t, capital T is f of little t, temperature is a function of time. It may be that temperature rises 12 degrees in 1 hour. That's an average of 12 degrees per hour for the average rate of change of temperature during the entire hour, which probably means that the temperature was rising maybe slower than 12 degrees per hour for part of the time and faster than 12 degrees per hour at other points in that time. This leads to questions then about the instantaneous rate of change of temperature at each particular point in time. This quantity is called a derivative, and the process of computing the derivative is known as differentiation. Now, the second branch of calculus is integration, introduced sometime around the end of the first and the beginning of the second semester. Suppose water flows into a tank at a rate of 12 gallons per hour. That means every hour, the amount of water in the tank increases by 12 gallons. However, suppose that water is flowing into the tank at a variable rate of r of t gallons per hour at each point in time t. When the rate r of t is not constant, we can't just multiply rate times time. The total amount of water flowing into the tank is the integral of r of t with respect to the time t, say from some starting time t0 to some final time t1. The process of computing this integral is called integration. So an integral is actually the value of some quantity that is accumulating at a variable rate. Before defining derivatives and integrals, we must first understand the most basic notion of calculus, which is the notion of a limit. This underlies all of calculus. Both the derivative and the integral are defined using certain limits. And limits are also important, very important in their own right, not just as a stepping stone to derivatives and integrals. There's also another important topic arising in second semester calculus, the notion of a power series. Think of a power series as something like a polynomial, but with infinitely many terms. Of course, a polynomial has only finitely many terms. This allows us to greatly expand the kind of functions we can consider far beyond the elementary algebraic and transcendental functions that we were able to work with. This is the larger class of so-called analytic functions. It still doesn't actually include all the real-life functions, but it's such a large class that it will suffice for many of our purposes. Also in third semester calculus, we encounter power series in several variables. In both the single variable and multivariable cases, power series can be seen as a kind of limit of polynomials. And that's calculus in a nutshell.